Mm. Hello everyone. In this video, we are implementing the trigonometric function link network in Simulink for nonlinear system identification. Later on, we will compare its performance with MATLAB code results also. Uh, Let us begin with how we created the input data. So we used uh, 10 to the power 5 random input samples and then generated the uh, Gaussian noise, and both input and noise signals were passed into Simulink using Brown workspace block. Both of these will be here. Then the input is processed by the buffer to create delayed version of this. Then the function expansion block, uh, we are using a 10 tap second order TFLN. So expansion block, here we apply the nonlinear transforms to buffer input. So uh, as you can see, here we will have the sine pi of buffered version of the input, then cos pi of function, and sine 2 pi of function, and cos 2 pi of function. And as the expanded version of the input, we will have one bias, then this buffered version of the input signal, and then this nonlinear function applied input signal. So overall, here we will have one of buffered signal, and then this nonlinear function applied signal, and then we will have the dot product with the weight vector uh, to get the TFLN output. So for the weight vector, we are using data memory block. So first one, we will initialize it with the zero value, and uh, then for the to use the FLN weight values, we will use data store read block, and to store back the updated values of the weights, we will use data store, right? And uh, I will come to the weight update parts in a bit. So first, let me show you the how we are generating the our desired signal for the error calculation. So in this MATLAB function block, the desired signal uh, is created like using these nonlinear relations, and then the desired output is then combined with the noise and choose to calculate the error between predicted and the output of the predicted will be uh, we can say the instead of predicted we will say the TFLN output. So this will be desired signal minus TFLN output will give us error, and then the we will use the error for the weight update, and also uh, the output error is also stored for comparison with MATLAB results in the workspace. Then now comes to the uh, weight update uh, rules. So in the weight update rule, we use gradient descent method, and cost function, again we are using mean square error minimization. So simply our weight update rule will be the previous value uh, will be added with the error uh, error multiplied by the function expanded input, and there will be one learning rate and some constant. So 2 times learning rate multiplied by the error multiplied with the expanded input. So expanded input means output at this stage of the TFLN. So then after combining the previous and the this update according to this update rule, we will store the updated uh, uh, weight values to the this data store, right? Using data store, right, we will have the new updated uh, weight values. So let me run this code. So this is compiling, and here you can see the weight values are getting updated, and the error will be stored uh, in our workspace. So here is the stored error values over the inputs. So we will use to compare it with the TFLN MSC. So this is the code for TFLN, and again we are using the same second order 10 type TFLN in the code also, and the same learning rate. And at the end, we will compare the MSC of the both the TFLN with code and Simulink logs. Let me run this. So you can see in the plot, this plot compares the MSC for both MATLAB code and our Simulink model. So as you can see here also, uh, the Simulink output closely matches the MATLAB output, validating our implementation. So that's the TFLN with the Simulink logs. Thank you.